Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the weight of the day start to lift from your shoulders. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the universe feels both impossibly far and somehow close? Tonight we're going to explore what happens when humanity builds a telescope so powerful that it can see farther back in time than anything before it, to moments just after the universe itself began. We'll discover what the James Webb Space Telescope found when it looked into that ancient darkness, understand why those discoveries have scientists questioning everything they thought they knew about cosmic history, and contemplate what it means when our instruments reveal a universe stranger and more wondrous than our theories predicted. It's a journey that spans 13 billion years, from the present moment all the way back to the cosmic dawn. But don't worry, this isn't going to be a frightening exploration of cosmic horror or an anxiety-inducing journey into the unknown. Instead, we'll move slowly and carefully through the telescope's discoveries, the science that makes them possible, and the quiet revolution happening in astronomy right now. By the end, I think you'll find there's something deeply peaceful in knowing that the universe still holds mysteries, still has the power to surprise us. If you enjoy these calm explorations of cosmic wonder, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for being part of this community of cosmic contemplation. So settle in, let your shoulders drop, take a slow breath. And let's begin our slow drift through the deepest images ever captured, through time itself, to the very edge of what we can know. There's nowhere you need to be right now. Nothing you need to do, just listen and let the story of our universe unfold. To understand what the James Webb Space Telescope found, we first need to understand what it is, how something built by human hands can look backward through time itself. Picture, if you will, a mirror made of gold composed of 18 hexagonal segments that fit together like a honeycomb, each one polished to a precision that would make a single human hair seem mountainous by comparison. This mirror stretches 21 feet across, nearly 3 times the width of the Hubble Space Telescope that came before it, and it lives not in orbit around Earth, but at a point in space nearly 1 million miles away, a location where the gravitational pulls of Earth and Sun balance in a cosmic equilibrium. The choice of gold wasn't arbitrary or decorative. Gold reflects infrared light, the kind of light that reaches us from the most distant objects in the universe, light that has been stretched and reddened by the expansion of space itself during its journey of billions of years. When something moves away from you, its light shifts toward the red end of the spectrum, a phenomenon called redshift. And the farther away something is, the more space has expanded during the light's journey, the redder that light becomes. The most distant galaxies aren't just far away in space, they're far away in time, and their light has been travelling so long that it's shifted entirely out of the visible spectrum and into the infrared, invisible to human eyes but perfectly visible to Webb's golden gaze. Building this mirror required a new kind of precision. Each segment needed to be aligned to within a fraction of a wavelength of light, adjusting themselves with tiny motors that can move in steps measured in nanometers, billionths of a meter. The entire structure needed to unfold in space like an impossibly complex piece of origami, deploying a sunshield the size of a tennis court to keep the telescope cold enough that its own heat wouldn't overwhelm the faint infrared whispers from the ancient universe. Every part of this deployment needed to work perfectly, hundreds of steps that had never been tested together in actual space conditions. Any one of which could have failed and rendered the entire $10 billion investment useless. And yet, it worked. Through what can only be described as a combination of engineering brilliance and extraordinary fortune, every single deployment step succeeded. The mirror unfolded, the segments aligned, the instruments cooled to their operating temperatures just a few degrees above absolute zero. and the telescope opened its golden eye on a universe waiting to be seen in a new way. The first images came back showing stars sharper than ever before, galaxies appearing as jewelled spirals and ellipses against the darkness, and in the backgrounds of those images, in the spaces between the bright objects, tiny smudges and dots that turned out to be something no one quite expected. What Webb could do that Hubble couldn't was look deeper into the infrared, see farther back in time, catch photons that had been travelling through expanding space for so long that they'd shifted entirely beyond visible light. Every telescope is a time machine, showing us the universe not as it is, but as it was when the light left its source. The sun as it was 8 minutes ago, stars as they were years or centuries ago, distant galaxies as they were millions or billions of years ago. But Webb could look farther back than anything before it, back to a time when the universe itself was young, when the first stars and galaxies were just beginning to form. And this brings us to something equally remarkable. What happens when you point such an instrument at the sky and let it stare at a single patch of darkness for hours or days, gathering every photon it can catch? The Hubble Deep Field did this in the late 1990s, pointing at a seemingly empty patch of sky for 10 days and discovering thousands of galaxies where there had appeared to be nothing. Webb was designed to do the same thing, only deeper, farther, earlier. The scientists selected targets, planned observations, and waited for the data to arrive, expecting to see the universe's first galaxies appearing as faint primitive smudges from the cosmic dawn. What they saw instead was something that didn't quite fit the models, galaxies that appeared too bright, too large, too structured for how early in cosmic history they existed. And that's where our story truly begins. To appreciate what Webb discovered, we need to travel backward in time, not through space but through understanding, to a moment 13.8 billion years ago when the universe began. Not in a place, but everywhere at once, space itself expanding from a state of unimaginable density and heat. A moment that physics calls the Big Bang, even though it wasn't an explosion in any conventional sense, but rather the beginning of space and time themselves. In those first moments, the universe was too hot for atoms to exist. Matter consisted of a plasma of fundamental particles. Electrons and quarks and photons all mixed together in a state so energetic that nothing stable could form. But the universe was expanding, and as it expanded it cooled, and after about 3 minutes it became cool enough for the first atomic nuclei to form, mostly hydrogen and helium, the simplest elements. Still, it remained too hot for electrons to settle into orbits around these nuclei, too hot for actual atoms to exist. For nearly 400,000 years, the universe remained this way, a fog of plasma through which light could not travel freely, photons constantly scattering off free electrons in an opaque cosmic soup. But expansion continued, cooling continued, and eventually the universe reached a temperature where electrons could finally settle into stable orbits around atomic nuclei, forming the first actual atoms. At that moment, light was suddenly free to travel through space unimpeded, and the universe became transparent. This moment, called recombination, left an imprint that we can still see today. Those first free photons travelling through space for 13.8 billion years have been stretched by the expansion of space into microwave wavelengths, forming what we call the cosmic microwave background, a faint glow of ancient light coming from every direction in the sky. This radiation, discovered in 1965, is the afterglow of the Big Bang itself, the oldest light we can see. A snapshot of the universe when it was just 400,000 years old. After recombination came a period that astronomers call the Dark Ages, not because anything sinister was happening, but because there were no stars yet, no galaxies, nothing to produce visible light. The universe consisted of vast clouds of hydrogen and helium gas, slowly collapsing under their own gravity, growing denser in some regions while leaving others relatively empty. these density variations, tiny fluctuations that had existed since the earliest moments after the Big Bang, were the seeds from which all structure would eventually grow. Gravity pulled gas into increasingly dense clumps, and as these clumps grew denser, they grew hotter, pressure building at their cores. Eventually, somewhere in the universe, a cloud of gas became dense enough and hot enough that nuclear fusion ignited at its core, hydrogen atoms fusing into helium and releasing energy. And the first star was born. We don't know exactly when this happened, somewhere between 100 million and 200 million years after the Big Bang, but whenever it occurred, it marked the end of the Dark Ages and the beginning of what astronomers call the cosmic dawn. These first stars were likely very different from the Sun, probably much more massive, burning much hotter and brighter, living fast and dying young in spectacular supernovae that scattered heavier elements into space. They lived in small groups and clusters that would eventually merge and grow into the first galaxies, collections of millions or billions of stars bound together by gravity. Theory suggested these first galaxies would be small and irregular, chaotic collections of stars still in the process of assembling into organised structures. The James Webb Space Telescope was specifically designed to find these first galaxies, to see light from the cosmic dawn, to watch the universe's earlier structures forming. Scientists planned observations targeting the period from about 100 million to 500 million years after the Big Bang, expecting to find faint, small primitive galaxies appearing in Webb's deep images. They had models predicting what these galaxies should look like, how bright they should be, how massive they could have grown in the limited time available. And then Webb started sending back data. Images of unprecedented depth showing the universe when it was younger than it had ever been seen before, and those images contained galaxies that didn't quite match the predictions, objects that seemed to challenge our understanding of how quickly structure could form in the early universe. Let that thought settle as we continue. The first hints came from Webb's early release science program. Observations designed to test the telescope's capabilities and provide the astronomical community with data to work with. Scientists pointed Webb at regions of sky that Hubble had already observed deeply, places like the Goods Fields and the Hubble Ultra Deep Field, expecting to see fainter, more distant galaxies beyond what Hubble could detect. What they found exceeded expectations in an unexpected way. Among the new galaxies appearing in Webb's images were objects showing spectral signatures, indicating they existed when the universe was between 200 million and 500 million years old, shockingly early in cosmic history. But these weren't the faint, small, primitive structures the models predicted. Some of them appeared remarkably bright, shining with the light of billions of stars, seeming to have assembled enormous amounts of mass far earlier than theoretical models suggested was possible. One galaxy in particular, initially catalogued as GLASS-z13, appeared to exist just 300 million years after the Big Bang. Yet it shone with a luminosity suggesting it contained about 1 billion times the mass of our Sun in stars. To put that in perspective, the models predicted galaxies at that epoch should be much smaller, perhaps containing a few 100 million solar masses at most. The difference might seem subtle, but in the early universe, every additional million years of time is crucial. And having galaxies form faster and grow larger than predicted suggests something significant about how structure assembled in those first cosmic moments. More galaxies followed in the data, objects at redshifts indicating they formed between 300 million and 500 million years after the Big Bang, many of them brighter and seemingly more massive than the models comfortably allowed. Some showed surprisingly high levels of chemical enrichment, containing elements heavier than hydrogen and helium, in amounts that suggested multiple generations of stars had already lived and died, processing primordial gas into heavier elements through nuclear fusion and scattering those elements through supernova explosions. The scientific community responded with both excitement and caution. Initial distance estimates for galaxies are made using photometry, analysing how bright an object appears in different wavelength filters. a technique that works well but can sometimes be fooled. A relatively nearby dusty galaxy, reddened by dust absorption, might appear similar to a much more distant pristine galaxy whose light has been redshifted by cosmic expansion. Confirmation requires spectroscopy, splitting the light into its component wavelengths and looking for specific spectral features that can only appear at certain redshifts. As spectroscopic follow-up observations accumulated, some of the earliest galaxy candidates were confirmed at their extreme distances, while others turned out to be closer, less remarkable objects that had been misidentified. But enough of the distant galaxies remained confirmed to present a genuine puzzle. The universe seemed to have assembled galaxies faster and more efficiently than the models predicted. Building massive structures in what should have been insufficient time, the challenge comes down to a fundamental limit on how quickly galaxies can form. After the Big Bang, matter existed primarily as diffuse gas spread throughout space. For this gas to form galaxies, it needed to collapse under gravity into dense clumps, and gravity can only pull things together so quickly. The rate of collapse depends on the density of matter, and while dark matter can collapse freely, the normal matter that forms stars also experiences pressure from heat and radiation that resist collapse. There's effectively a speed limit on how fast gas can cool, condense and form stars. Additionally, the first stars needed to form, live out their lives, and die before they could enrich the gas with heavier elements. The most massive stars live only a few million years, but even so, building up multiple generations of stars, each one enriching the gas a bit more, takes time. Finding galaxies showing substantial chemical enrichment just a few 100 million years after the Big Bang suggests the first stars formed earlier than expected, or that star formation proceeded more rapidly than the models allowed, or both. Some astronomers began to wonder if the models needed revision, if perhaps our understanding of how efficiently gas could cool and form stars in the early universe was incomplete, if feedback processes that regulate star formation in later cosmic epochs were less effective in the beginning. Others suggested that perhaps dark matter behaved differently in the early universe, or that the initial density fluctuations seeding galaxy formation were larger than observations of the cosmic microwave background seemed to indicate. But there's another dimension to consider here, something that makes the observations even more intriguing and potentially more challenging for standard cosmology. And that's the structure of these early galaxies themselves. When astronomers looked more carefully at the detailed structure of some of Webb's earliest galaxies, they found another surprise. These weren't just brighter and more massive than expected. Some of them showed morphological features suggesting a level of organization and structure that seemed premature for their cosmic age. Galaxy formation theory suggests that the first galaxies should be small, irregular, chaotic systems, clumps of stars and gas still in the process of merging and assembling into organized structures. Only later, after hundreds of millions or even billions of years of evolution, mergers and gravitational settling, should galaxies develop the organized structures we see in the later universe, the beautiful spiral arms of disk galaxies, or the smooth elliptical shapes of older systems. But some of Webb's early galaxies showed hints of structure that seemed too organized, too settled for their age. Disk-like shapes appeared in some systems, suggesting gas had already settled into rotating configurations. Others showed evidence of stellar bars, elongated structures of stars that form in the centres of disk galaxies and require a fairly settled, stable gravitational environment to persist. These features aren't impossible in young galaxies, but they're unexpected, suggesting that the process of galaxy assembly and settling happened faster in the early universe than our simulations predict. The simulations themselves are sophisticated pieces of computational cosmology, vast computer models that follow the evolution of dark matter and normal matter from shortly after the Big Bang through billions of years of cosmic history. They incorporate our best understanding of gravity, hydrodynamics, star formation, supernova feedback, black hole growth, and all the complex physics that shapes how galaxies form and evolve. When these simulations are run forward in time, they generally do a good job of reproducing the universe we see around us today, the distribution of galaxies, their properties, their evolution. But when you look at what these simulations predict for the very early universe, for the first few 100 million years after the Big Bang, they tend to show small, irregular protogalaxies still in the early stages of assembly. The galaxies Webb observed seemed more evolved, more organised, as if they had had more time to settle than they actually had. It's as though the universe was in a hurry to build structure, to organise matter into galaxies faster than gravity alone should have allowed. One possible explanation involves the role of dark matter in the early universe. Dark matter, the invisible substance that makes up about 85% of all matter in the universe, can collapse under gravity without being impeded by pressure or radiation the way normal matter is. It forms the gravitational scaffolding into which normal matter falls, creating the potential wells that become the sites of galaxy formation. If dark matter clumped more efficiently in the early universe than we think, perhaps due to properties we don't fully understand, it might have created deeper gravitational wells earlier, allowing normal matter to fall in and form stars more quickly. Another possibility involves the initial conditions of the universe itself. The cosmic microwave background tells us about the density fluctuations present when the universe was 400,000 years old, the seeds from which all structure grew. But those observations have limited resolution and can only see fluctuations above a certain size. If there were additional small-scale fluctuations that we can't see in the microwave background, they might have allowed structure to form faster on small scales, building galaxies earlier than our models predict. There's also the question of how the first stars formed and how they influenced their surroundings. The theoretical predictions for the first stars suggest they were very massive, perhaps 50 to 100 times the mass of the Sun, burning incredibly hot and bright and living for only a few million years before exploding as supernovae. These stars would have produced intense ultraviolet radiation that ionized the gas around them, creating bubbles of ionized hydrogen that expanded and eventually overlapped, reionizing the entire universe. This reionization process had profound effects on galaxy formation. The ultraviolet radiation heated the gas, making it harder for gravity to pull it into small clumps, effectively preventing the formation of very small galaxies. But the timing and details of reionization depend on when and how the first stars formed, and if that process happened differently than we think, it could have allowed more or less efficient galaxy formation in those critical early epochs. What's emerging from Webb's observations is not a picture that completely overturns cosmology, but rather one that suggests our models of the early universe might be missing important details, might not fully capture the complexity and efficiency with which the first galaxies formed. The observations are pushing theorists to reconsider assumptions, to look for mechanisms that might allow faster structure formation, to explore parameter spaces in their models that previously seemed unnecessary. And this brings us naturally to consider another aspect of these early galaxies that has surprised observers, something hidden in the light itself. When astronomers analyse the light from distant galaxies, they're not just measuring brightness and colour, they're reading a detailed chemical signature, a record of every element present in the stars and gas of that galaxy. This is possible because each element absorbs and emits light at specific wavelengths, creating a unique spectral fingerprint. Hydrogen produces certain spectral lines, oxygen produces others, carbon, nitrogen, iron. Each element leaves its mark on the light passing through or emitted by a galaxy. The universe began with almost nothing but hydrogen and helium, the simplest elements, created in the first few minutes after the Big Bang, when the universe was still hot enough for nuclear fusion to occur everywhere. Everything heavier than helium, all the carbon and oxygen and iron and gold, every element essential to planets and life, was created later, forged in the nuclear furnaces of stars or in the explosive deaths of massive stars as supernovae. This means the very first stars had to be composed almost entirely of hydrogen and helium. what astronomers call population 3 stars, purely primordial objects never yet observed but predicted by theory. These stars would have behaved differently from modern stars because the presence of heavier elements affects how stars form, how they burn, how they evolve. When these first stars died, they scattered trace amounts of heavier elements into space, enriching the gas from which the next generation of stars would form. Each subsequent generation of stars inherited a slightly higher abundance of heavy elements, building up what astronomers call metallicity over cosmic time. Our Sun, forming about 4.6 billion years ago, inherited heavy elements from multiple generations of stars that lived and died before it, giving it about 2% heavy elements by mass. The very oldest stars in our galaxy, formed when the Milky Way itself was young, contained far less, perhaps a few hundredths or even thousandths of a percent heavy elements. When Webb's spectroscopic observations started revealing the chemical composition of galaxies from the first few hundred million years after the Big Bang, astronomers expected to see very low metallicities, evidence that only one or perhaps two generations of stars had lived and died. But some of the observed galaxies showed higher metallicities than expected, suggesting more extensive chemical enrichment than seemed possible in the available time. The challenge is that chemical enrichment requires multiple cycles of star formation and death. Massive stars can live and die in just a few million years, enriching the surrounding gas with the products of their nuclear burning and supernova explosions. But this enriched gas then needs to cool, collapse, and form new stars, which themselves need time to evolve and produce their own heavy elements. Each cycle takes time, and while a few cycles can occur within a few hundred million years, building up substantial heavy element abundances requires either very efficient cycling or an earlier start to star formation than the models predict. Some of the early galaxies also showed evidence of specific elements that are particularly hard to produce quickly. Nitrogen, for instance, is primarily created in intermediate mass stars that take longer to evolve than the most massive stars. Finding significant nitrogen in galaxies just a few hundred million years old suggests that star formation began early enough for even these slower evolving stars to have contributed to the chemical mix. There are ways to potentially explain higher than expected metallicities without invoking dramatic changes to cosmology. Perhaps the first stars were not all extremely massive. Maybe some smaller, longer-lived stars formed alongside the giants, allowing for more continuous chemical enrichment. Or perhaps supernova explosions were more efficient at mixing heavy elements through the gas than simulations suggest, spreading enriched material more widely and allowing it to be incorporated into new stars more quickly. Another possibility involves what astronomers call population 3.5 stars, a hypothetical intermediate generation between the purely primordial first stars and the metal-enriched stars that came later. These stars might have formed from gas that was slightly enriched by the first supernovae, just enough to change their formation and evolution in ways that allowed for more efficient chemical processing. The observations don't prove any single explanation. They simply show that the early universe was chemically enriched faster than the simplest models predict, adding another piece to the puzzle of how the first galaxies assembled and evolved. Combined with the observations of unexpectedly massive and structured galaxies at early times, a picture emerges of an early universe that was more active, more efficient at forming stars and building galaxies than our models quite capture. This has led some astronomers to propose modifications to the standard cosmological model, tweaks to parameters, or inclusion of new physics that might allow for faster structure formation. Others argue that the observations can be explained within the standard model if we're more careful about accounting for uncertainties, and if we recognise that our models of the early universe are still works in progress, less refined than our models of later cosmic epochs simply because we've had fewer observations to constrain them. And perhaps this is what matters most as we move forward through this exploration. The recognition that science progresses not through having all the answers, but through observations that challenge our understanding, that push us to look more carefully, to question our assumptions, to refine our models. The universe is under no obligation to match our expectations, and when it surprises us, that's when we learn the most. Let that thought settle as we move into our next act. To understand the full significance of what Webb found, we need to explore how astronomers measure distances to objects billions of light years away, how they determine when in cosmic history a distant galaxy existed. The technique relies on redshift, the stretching of light as it travels through expanding space. But the details involve a sophisticated combination of observation and theory. When light travels through expanding space, its wavelength increases proportionally to how much space has expanded during its journey. A galaxy whose light has been travelling for 10 billion years has its wavelength stretched by a factor, corresponding to how much the universe has expanded in those 10 billion years. Astronomers quantify this stretching with a number called redshift, usually denoted by the letter Z. Where Z equals 0 means no redshift at all, the object is nearby, and larger values of Z correspond to greater distances and earlier cosmic times. The relationship between redshift and distance depends on the expansion history of the universe, which in turn depends on what the universe contains and how those contents affect the expansion. A universe dominated by matter expands differently than one dominated by radiation or dark energy. And measuring the redshifts of many objects at various distances allows astronomers to map out this expansion history and infer the universe's composition. For the closest galaxies, redshift can be measured with great precision using spectroscopy. The light from a galaxy contains spectral features, emission or absorption lines created by specific elements, and these features appear at very precise wavelengths in laboratory conditions. When we see the same features in a distant galaxy's spectrum but shifted to longer wavelengths, we can calculate exactly how much the wavelengths have been stretched, and thus determine the redshift precisely. But spectroscopy requires collecting a lot of light, enough to spread into a spectrum and reveal these detailed features, and for very distant, very faint galaxies. This can require hours or even days of observation time with the largest telescopes. To make initial surveys and identify interesting distant galaxy candidates, astronomers often use photometry instead, observing how bright an object appears through various filters that let through light in different wavelength ranges. By comparing an object's brightness in multiple filters, astronomers can roughly estimate its redshift based on how its brightness changes with wavelength. A technique called photometric redshift estimation. This works because galaxies have characteristic spectral features, like the Lyman break, where hydrogen suddenly starts absorbing ultraviolet light, and by seeing where these features fall in the observed wavelengths, you can estimate the redshift. But photometry is less precise than spectroscopy, and can sometimes be fooled by objects whose intrinsic spectral shapes are unusual. When Webb's first deep images revealed candidate galaxies at redshifts of 13, 14, even 16, these were photometric estimates, carefully calculated but subject to uncertainties. The astronomical community recognised that some of these candidates might turn out to be closer objects masquerading as distant galaxies, perhaps dusty galaxies whose intrinsic red colours mimicked the appearance of red-shifted pristine galaxies. As spectroscopic follow-up observations accumulated, using Webb's spectroscopic instruments to gather detailed spectra of the candidate galaxies, some were confirmed at their extreme distances, while others were revealed to be less distant. A galaxy initially thought to exist at redshift 16, corresponding to just 250 million years after the Big Bang, might turn out to be at redshift 7, still distant but from a much later cosmic epoch, giving much more time for it to have formed and assembled its mass. This process of confirmation and revision is normal in astronomy, part of how the field progresses, and it's important not to see it as the observations being wrong, but rather as understanding being refined. The initial photometric estimates were reasonable given the available data, and spectroscopic follow-up provides more precise measurements. What matters for our story is that even after accounting for revised distance estimates, Even after excluding candidates that turned out to be closer than initially thought, a substantial population of very distant galaxies remained confirmed, galaxies existing when the universe was between 200 million and 500 million years old, many of them brighter and more massive than the models comfortably predicted. The confirmed observations established that the universe was forming substantial galaxies earlier and more efficiently than expected. And this raised genuine questions about whether our models needed revision. But before concluding that cosmology needs dramatic changes, scientists needed to explore whether more subtle factors might explain the observations within the existing framework. One consideration involves dust, tiny solid particles made of carbon or silicates that form in the atmospheres of cool stars and in supernova ejetions. Dust absorbs and scatters light, reddening it the same way Earth's atmosphere reddens sunlight at sunset, and a dusty galaxy can appear redder and fainter than it would be if pristine. In the early universe, galaxies weren't expected to contain much dust, because dust is made from heavy elements, and the early universe had low metallicity. But if some early galaxies formed stars more rapidly than expected, quickly building up heavy elements and producing dust, they might appear redder than expected for their metallicity, potentially affecting photometric redshift estimates. Additionally, dust obscures ultraviolet light while allowing infrared light through, meaning a dusty galaxy might appear fainter in ultraviolet and brighter in infrared than a pristine galaxy at the same distance, changing how we interpret its intrinsic luminosity. Another factor involves the initial mass function, the distribution of stellar masses in a forming stellar population. Modern star-forming regions produce mostly low-mass stars with smaller numbers of high-mass stars, following a distribution called the Salpeter initial mass function. But the first stars, forming from pristine gas with no heavy elements, might have followed a different distribution, perhaps forming more massive stars than later generations. If the early universe preferentially formed massive stars, galaxies would appear brighter for a given total mass, because massive stars are much more luminous than low-mass stars. These considerations don't eliminate the puzzle entirely, but they illustrate how complex the interpretation of observations can be. How many factors need to be considered when trying to understand what we're seeing? The universe revealed by Webb is definitely challenging our models, but whether it's fundamentally overturning cosmology or simply requiring refinements to our understanding of galaxy formation remains an open question, one that astronomers continue to explore. Which leads us to another aspect of Webb's discoveries, something that connects to the very large-scale structure of the universe. The universe at large scales is not uniform but structured. Galaxies clumped into groups and clusters, these clusters connected by filaments of galaxies stretching across hundreds of millions of light-years, all surrounding vast voids that contain relatively few galaxies. This structure, called the cosmic web, formed through gravitational instability acting on the slight density fluctuations present in the early universe, denser regions pulling in more matter and growing denser still, while underdense regions became voids. The formation of this structure takes time, governed by how fast matter can collapse under gravity. Observations of the cosmic web in the relatively nearby universe, looking at cosmic times corresponding to when the universe was a few billion years old, show a well-developed web of filaments and clusters. But when we look farther back in time, to earlier cosmic epochs, we expect to see less developed structure, smaller groups of galaxies still in the process of assembling into larger clusters. Webb's observations have started to reveal what the cosmic web looked like in the very early universe, in those first few 100 million years after the Big Bang, and here too there are hints that structure might have developed faster than expected. Some of Webb's deep fields show concentrations of early galaxies that appear to be part of emerging filamentary structures, multiple galaxies at similar redshifts and in close proximity on the sky, suggesting they're part of overdense regions that would eventually become galaxy clusters. Finding such structures so early is not impossible. but it requires that the initial density fluctuations seeding these structures were large enough and that gravity had sufficient time to pull matter together into these concentrated regions. The size of initial fluctuations is constrained by observations of the cosmic microwave background, which maps the density variations present when the universe was 400,000 years old. Those observations set limits on how lumpy the early universe could have been. If the observed early structures turn out to be denser or more developed than what the measured fluctuations in the microwave background should produce by the time the universe was a few 100 million years old, it would suggest either that our understanding of how structure grows is incomplete, or that there were additional fluctuations on smaller scales that the microwave background observations can't see. Dark matter plays a crucial role in this story because it can collapse under gravity without being impeded by pressure or radiation, forming the gravitational wells into which normal matter falls. The properties of dark matter, how it clumps and how its clumps evolve, directly affect how quickly structure forms. The standard model assumes dark matter is cold, meaning its particles move slowly compared to the speed of light, which allows it to clump efficiently on all scales. But there are alternative models where dark matter has different properties, perhaps being warm rather than cold, moving faster and thus not clumping as efficiently on small scales, or perhaps interacting with itself through some unknown force, changing how it collapses. These alternative dark matter models predict different structure formation histories, and in principle, observations of when and how structure formed in the early universe could help distinguish between them. The challenge is that the differences between models are often subtle, and observational uncertainties are still large enough that definitive statements are difficult. What we can say is that Webb's observations of early structure formation are providing new constraints, new data points that theorists need to match with their models, and in doing so they're helping refine our understanding of dark matter and structure formation. There's something almost poetic about this process, the way observations and theory interact, each pushing the other forward. Observations reveal phenomena that theory must explain, and theory makes predictions that observations must test. Neither can progress far without the other, and the tension between them, the observations that don't quite fit the models, is where the most interesting science happens. In the case of early structure formation, we're watching this process unfold in real time as new Webb observations come in, and theorists work to understand them, running new simulations with different parameters, exploring different physical processes that might allow for faster or more efficient structure formation. Some proposed mechanisms involve enhanced cooling of gas in the early universe, perhaps through processes involving hydrogen molecules that form in specific conditions, allowing gas to collapse more efficiently into stars. Other proposals involve the role of the first supermassive black holes, objects millions or billions of times the mass of the Sun that sit at the centres of most large galaxies. These black holes grow by accreting matter, pulling in gas and stars from their surroundings, and as matter falls toward a black hole, it heats up and releases enormous amounts of energy. This energy can have profound effects on the surrounding galaxy, heating gas and preventing it from forming stars, or, alternatively, compressing gas and triggering bursts of star formation. The origin of supermassive black holes is itself a puzzle. Growing a black hole from a stellar mass seed, perhaps a few tens of times the mass of the Sun formed when a massive star collapses, up to 1 million or billion solar masses, requires time and a continuous supply of matter to accrete. The growth rate is limited by radiation pressure from the accreting matter pushing outward, and calculations suggest that growing supermassive black holes in the first few 100 million years after the Big Bang is challenging with standard accretion models. Yet Webb has found evidence for supermassive black holes existing when the universe was very young, active galactic nuclei powered by black holes accreting matter when the universe was less than 1 billion years old. Some of these black holes appear to be more massive than expected for the age of the universe, adding another piece to the puzzle of how structure assembled so quickly in the early cosmos. And this connects to something we'll explore more deeply as we continue, the question of whether the universe had some mechanism for jump-starting structure formation, some process that allowed massive objects to form earlier than standard gravity alone would permit. The supermassive black holes that Webb has found in the early universe present their own profound puzzle, one that intertwines with the mystery of early galaxy formation. These objects, with masses millions or even billions of times that of our Sun, exist when the universe is less than 1 billion years old, and their presence demands explanations for how they grew so large so quickly. Black holes grow primarily through accretion, pulling in matter from their surroundings. As matter spirals toward the black hole, it forms an accretion disk where friction heats the material to millions of degrees, causing it to radiate enormous amounts of energy before finally falling through the event horizon. This radiation produces pressure that pushes outward on surrounding matter, and there's a fundamental limit, called the Eddington limit, on how fast a black hole can grow through accretion without the radiation pressure blowing away the infalling matter. For a black hole growing at the Eddington limit, starting from a seed mass of 10 or 100 times the mass of the Sun, typical of what a collapsing massive star might produce, reaching 1 million solar masses takes hundreds of millions of years. Reaching 1 billion solar masses takes longer still. This timeline is tight when you're trying to build supermassive black holes in the first billion years after the Big Bang, and finding billion solar mass black holes when the universe is only 700 million years old, as Webb has, requires either that the seed black holes were more massive than expected, or that they grew faster than the Eddington limit normally allows, or both. One possibility is that the seed black holes were not stellar remnants, but formed through a different mechanism called direct collapse. Under specific conditions in the early universe, a cloud of gas might collapse directly into a massive black hole without forming stars first, creating a seed with a mass of thousands or even tens of thousands of solar masses. Such seeds could then grow to supermassive scales more easily within the available time. Direct collapse requires special conditions, particularly a lack of heavy elements and molecular hydrogen, which normally help cool gas and allow it to fragment into individual stars. If the gas cannot cool efficiently, it stays hot and collapses as a single mass, potentially forming a massive black hole directly. But these conditions are rare, requiring that the gas has been bathed in ultraviolet radiation from nearby sources that destroys the cooling molecules while not triggering star formation itself. Another possibility involves super-Eddington accretion, where black holes grow faster than the standard limit. This can happen if the accretion is not spherically symmetric, if matter falls in preferentially from certain directions, allowing the black hole to grow more rapidly than the Eddington limit calculated for spherical accretion would suggest. Some theoretical models and simulations suggest that in the dense, gas-rich environments of the early universe, such super-Eddington growth might have been possible, at least for brief periods. There are also more exotic proposals, ideas that push at the boundaries of known physics. Perhaps primordial black holes formed in the very early universe. During the first seconds after the Big Bang from density fluctuations or phase transitions in the exotic conditions of that era, these primordial black holes could have masses ranging from tiny to substantial, and if some of them ended up in the centres of forming galaxies, they might serve as seeds for supermassive black hole growth. The observations themselves come from identifying active galactic nuclei, galaxies with extremely bright central regions powered by black holes actively accreting matter. The brightness and spectral characteristics allow astronomers to estimate the black hole mass and accretion rate, and when these estimates indicate million or billion solar mass black holes at redshifts corresponding to the first billion years, it challenges theorists to explain how such massive objects formed so early. What's particularly intriguing is that these early supermassive black holes don't exist in isolation. They're embedded in galaxies, surrounded by stars and gas, and their growth is intimately connected to the growth of their host galaxies. There appears to be a relationship between the mass of a galaxy's central supermassive black hole and the mass of the galaxy's bulge, the central concentration of stars, suggesting that black holes and galaxies grow together, each influencing the other's evolution. This coevolution happens through feedback, processes where the black hole affects its host galaxy and vice versa. When a supermassive black hole accretes matter rapidly, it releases enormous energy that can heat the surrounding gas, driving powerful winds that blow gas out of the galaxy, potentially shutting down star formation. Conversely, when gas falls into the galaxy's centre, perhaps during a merger with another galaxy, it can fuel both star formation and black hole growth simultaneously. In the early universe, this coevolution must have been particularly active, with galaxies and their black holes growing rapidly together. The fact that Webb finds both massive galaxies and massive black holes at early times suggests that whatever mechanism allowed rapid galaxy growth also allowed rapid black hole growth, or perhaps that the two processes were linked, with black holes playing a role in how their host galaxies assembled. Some models propose that the energy from accreting black holes, while capable of shutting down star formation in later cosmic epochs, might have enhanced star formation in the early universe by compressing gas clouds and triggering collapse. If true, this would represent a positive feedback loop where black hole growth promotes galaxy growth, which in turn provides more gas to feed the black hole, allowing both to grow faster than either could in isolation. The observations are still being analysed, the data still being interpreted. But what's clear is that the relationship between early galaxies and their central black holes is more complex and perhaps more intimate than previously thought. Understanding this relationship may be key to understanding how both galaxies and supermassive black holes formed and grew in the early universe. And this brings us to consider the broader theoretical framework within which these observations are being interpreted. The standard model of cosmology and the question of whether it needs revision or refinement to accommodate what Webb has found. The standard model of cosmology, usually called Lambda-CDM, has been remarkably successful at explaining a wide range of observations from the cosmic microwave background to the large-scale structure of the universe to the expansion history traced through distant supernovae. Lambda stands for the cosmological constant, a form of dark energy causing the universe's expansion to accelerate, and CDM stands for cold dark matter, the invisible matter that provides most of the gravitational pull-shaping cosmic structure. This model starts with the Big Bang, an initial state of extreme density and temperature from which space itself expanded and cooled. It includes inflation, a period of exponential expansion in the first fraction of a second that smoothed the universe and created the initial density fluctuations from quantum fluctuations stretched to cosmic scales. It describes how these density fluctuations grew under gravity, eventually forming the cosmic web of galaxies, clusters, and filaments we observe today. The model makes specific predictions about what the universe should look like at different cosmic times, how structure should grow, how galaxies should form and evolve, when the first stars should appear, how the cosmic microwave background should look. And for the most part, observations have matched these predictions remarkably well. The cosmic microwave background shows exactly the pattern of fluctuations the model predicts. The abundances of light elements created in the first few minutes after the Big Bang match the model's calculations. The distribution of galaxies on large scales matches what simulations based on the model produce. But the model also has free parameters, numbers that must be measured from observations rather than predicted from first principles. These include the total density of matter, the amount of dark energy, the rate of expansion, the amplitude of initial density fluctuations. By measuring these parameters with various observations and checking whether they're consistent, astronomers can test whether Lambda-CDM provides a coherent description of reality, and for the most part it does. Measurements of the cosmic microwave background by satellites like WMAP and Planck have determined these parameters with high precision, and when you use those parameters to predict other observations like the distribution of galaxy clusters or the relationship between distance and redshift, the predictions match what we observe. This internal consistency across many different types of observations is why Lambda-CDM has become the standard model. But no model is perfect, and there are some tensions, places where different observations seem to give slightly different values for the same parameter, or where predictions don't quite match observations at a detailed level. These tensions don't necessarily mean the model is wrong. They might reflect unrecognized systematic errors in observations or subtle effects not fully accounted for in the predictions. But they might also hint at physics beyond the standard model, new phenomena not captured in Lambda-CDM. Webb's observations of early galaxies add to these tensions, not dramatically but noticeably. The presence of massive, structured, chemically enriched galaxies when the universe is just a few 100 million years old pushes the boundaries of what Lambda-CDM comfortably predicts. The simulations based on Lambda-CDM can produce early galaxies, but typically not as massive or as evolved as some of what Webb observes. At least not in the abundance observed. This has led some astronomers to explore whether modifications to Lambda-CDM might better explain the observations. Perhaps the initial density fluctuations were slightly larger on small scales than the cosmic microwave background suggests. Perhaps dark matter has additional properties. Maybe it interacts with itself in subtle ways that affect how it clumps. Perhaps the first stars formed differently than assumed. Or perhaps there are feedback processes in the early universe that simulations don't yet capture properly. Others have proposed more radical changes, questioning whether dark energy was different in the early universe, or whether gravity itself behaves differently on cosmic scales than general relativity predicts. These proposals are more speculative, requiring not just changes to parameters but new physics, and they face the challenge of explaining not just Webb's observations, but all the other observations that Lambda-CDM successfully explains. The scientific process in these situations is one of careful evaluation, comparing how well different models match the full range of available data. Not just the latest observations, but everything accumulated over decades. A model that explains Webb's early galaxies but fails to match the cosmic microwave background, or the distribution of galaxy clusters, is not an improvement. The goal is a model that explains everything, or at least more than Lambda-CDM does, and finding such a model is challenging. What's perhaps most important to recognise is that science has been here before, confronted by observations that didn't quite fit the reigning models. Sometimes those observations led to revolutions, the discovery of new physics, fundamental changes in understanding. Other times they led to refinements, better measurements, improved models that extended the existing framework without replacing it. Distinguishing between these possibilities requires time, more observations, careful analysis. Webb is still early in its mission, with years of observations ahead. As more data accumulates, as more distant galaxies are found and studied, a spectroscopic follow-up confirms or revises initial photometric redshift estimates, the picture will become clearer. Perhaps the current tensions will resolve as we better understand the observations and refine our models. Perhaps they'll deepen, pointing toward genuine new physics. Either way, the process is exciting, representing cosmology at its best. Observations pushing theory, theory guiding new observations, both working together to reveal the universe's nature. And in this process, there's room for uncertainty, for acknowledging what we don't know, for holding space for questions while we work toward answers. Let that thought settle as we move forward. One area where our models of galaxy formation might be incomplete involves the complex physics of feedback, the ways in which star formation and black hole activity affect the gas from which galaxies form, regulating and sometimes shutting down the very processes that build galaxies. Understanding these feedback processes is crucial because they determine how efficiently gas can cool, collapse, and form stars, and getting the feedback right in simulations is one of the biggest challenges in computational galaxy formation. When massive stars form, they emit intense ultraviolet radiation that ionizes the surrounding gas, heating it and creating pressure that can blow gas out of the galaxy, or at least prevent it from collapsing further. When these massive stars die as supernovae, they inject energy and momentum into the interstellar medium, creating blast waves that sweep up and heat gas, again potentially preventing star formation. These processes are called stellar feedback, and they play a major role in regulating how galaxies convert their gas into stars. In the modern universe, observation suggests that galaxies convert only a small fraction of their available gas into stars each billion years, something like 1 to 5%, much lower than you'd calculate if you just considered gravity pulling gas into dense clouds where it forms stars. The difference is feedback, processes that heat gas, blow it out of the galaxy, or otherwise prevent it from forming stars. Without feedback, simulations produce galaxies that form stars too efficiently, building more massive galaxies than we observe and exhausting their gas supplies too quickly. But the effectiveness of feedback depends on the environment and conditions in which stars form, and these conditions might have been different in the early universe. The gas in early galaxies had lower metallicity, fewer heavy elements that facilitate cooling and dust formation, and this might have affected how efficiently stellar feedback operated. Perhaps the lower metallicity made feedback less effective, allowing early galaxies to form stars more efficiently than modern galaxies do. Alternatively, the first stars, if they were indeed more massive than modern stars, might have produced more intense feedback, more energetic supernova, more powerful ultraviolet radiation. This could have made feedback more effective, potentially slowing star formation, but it also might have heated the intergalactic medium more effectively, affecting how gas fell into galaxies and perhaps changing the overall efficiency of galaxy formation in ways that simulations don't fully capture. Black hole feedback adds another layer of complexity. When supermassive black holes accrete matter, they release enormous amounts of energy, far more than stellar processes, and this energy can drive powerful outflows that blow gas out of galaxies or heat it to temperatures where it cannot cool and form stars. In the modern universe, this black hole feedback appears to be crucial in explaining why the most massive galaxies stopped forming stars, shutting down despite having ample gas supplies. In the early universe, if supermassive black holes formed and grew rapidly as Webb's observations suggest, their feedback might have played an important role in regulating early galaxy formation. But the details are uncertain because the feedback depends on how the black hole accretes matter, whether it produces powerful jets or broad winds, how those outflows interact with the surrounding gas, whether they remove gas entirely or just heat it temporarily. Simulating all these processes requires immense computational resources because you need to follow physics operating on scales from individual stars just a few light years across, up to entire galaxies spanning hundreds of thousands of light years, and even the intergalactic medium extending millions of light years. Current simulations make approximations, using subgrid models to represent processes that occur on scales too small to resolve directly. And while these approximations are informed by physics and calibrated against observations, they're still approximations. Different simulation groups use different subgrid models, different ways of representing feedback, and not surprisingly, different simulations produce somewhat different results for early galaxy formation. Some simulations produce galaxies at early times that are fairly massive and bright, approaching what Webb observes, while others produce less massive, fainter systems. The differences often come down to how feedback is modelled, how efficiently stars are assumed to form, how black holes are represented. This diversity of simulation results is actually healthy for the field, because it reveals where uncertainties lie, where our understanding is incomplete. By comparing simulations with different assumptions to Webb's observations, theorists can learn which assumptions work better, which physical processes are most important, gradually refining the models toward more accurate representations of reality. One thing that's becoming clear from this work is that the early universe might have been a more violent, energetic place than later epochs, with more intense star formation, more powerful feedback, more rapid black hole growth, all happening in smaller volumes with higher densities. The first billion years of cosmic history might have been a phase of rapid, turbulent galaxy assembly, fundamentally different in character from the more sedate galaxy evolution we see in later times. If true, this would mean that we can't simply extrapolate our understanding of modern galaxy formation backward to understand the early universe. We need to account for the different conditions, the different physics, that operated when the universe was young. Webb's observations are providing the constraints needed to develop this understanding, showing us what early galaxies actually looked like, allowing theorists to test their models against reality. And as we develop better models of feedback and early galaxy formation, we're also gaining insights into other aspects of the early universe, particularly the process of Reionization, when the first stars and galaxies produced enough ultraviolet radiation to ionize all the hydrogen in the intergalactic medium, transforming the universe from neutral to ionized. This process connects intimately to early galaxy formation because galaxies are the sources of the ionizing radiation. And understanding when and how Reionization occurred requires understanding when and how the first galaxies formed. Which brings us naturally to our next act, where we'll explore what Webb has revealed about this cosmic transformation, this moment when light conquered darkness and made the universe transparent once more. After the cosmic microwave background was released, after the universe became transparent to light for the first time about 400,000 years after the Big Bang, the cosmos entered a period astronomers call the Dark Ages, a time when no stars yet existed to produce visible light, when the universe consisted of vast clouds of hydrogen and helium slowly collapsing under their own gravity, growing denser in some regions while leaving others relatively empty. This period lasted for tens or perhaps 100 million years, a substantial fraction of the time from the Big Bang to now compressed into an epoch we've never directly observed. Can't directly observe because there were no sources of light to see. We infer what must have happened during the Dark Ages from theory, from understanding how gravity works and how gas behaves, but we don't have observations of this period itself. The Dark Ages ended when the first stars formed, when enough gas collected in the densest regions to ignite nuclear fusion, creating the first sources of light since the Big Bang's initial glow. These first stars, as we've discussed, were likely very massive and very hot, burning brightly but briefly, living perhaps only a few million years before exploding as supernovae, scattering the products of their nuclear burning into space and seeding the next generation of star formation with the first heavy elements. The light from these first stars was primarily ultraviolet radiation, photons energetic enough to ionize hydrogen, splitting hydrogen atoms into protons and free electrons. Around each star a bubble of ionized hydrogen formed, expanding outward as more ultraviolet photons were emitted, gradually growing larger as long as the star continued to shine. At first, these bubbles were isolated, scattered through the universe wherever the first stars formed, separated by vast expanses of neutral hydrogen. But as more stars formed, more bubbles appeared, and they began to overlap, merging into larger ionized regions. The process was hierarchical, small bubbles merging into larger bubbles, which merged into still larger regions, gradually transforming the entire universe from neutral to ionized. This process is called Reionization, even though it's the second time the universe became ionized, the first being in the hot dense plasma before recombination. Reionization was completed sometime before the universe was about 1 billion years old. We know this from observations of distant quasars, extremely bright objects powered by supermassive black holes, whose spectra show that the intergalactic medium along our line of sight is fully ionized. But the details of reionization, when it started, how long it took, what sources provided the ionizing radiation, these remain active areas of research. The timing depends on when the first stars and galaxies formed, how many ionizing photons they produced, how those photons escaped from galaxies into the intergalactic medium. The process depends on the topology of the ionized regions, whether reionization proceeded uniformly throughout space, or whether it happened in some regions before others, creating a patchy ionization state for an extended period. Webb's observations are helping to constrain this process by finding galaxies at the epoch when reionization occurred, measuring how many galaxies existed at different times, estimating their star formation rates and thus their production of ionizing photons. By comparing the observed population of early galaxies to what's needed to reionize the universe, astronomers can test whether galaxies alone could have provided sufficient ionizing radiation, or whether other sources might have been necessary. The observations suggest that galaxies, particularly numerous small galaxies that were too faint for Hubble to detect, probably provided most of the ionizing photons needed for reionization. But the efficiency of this process depends on how many of the ionizing photons produced in galaxies actually escaped into the intergalactic medium, rather than being absorbed by gas and dust within the galaxies themselves. In modern galaxies, most ionizing photons are absorbed internally, never escaping to affect the intergalactic medium. But early galaxies might have been more porous, with lower dust content and more turbulent gas distributions creating channels through which ionizing photons could escape. Webb is observing galaxies at the epoch of reionization, specifically to measure these escape fractions, to determine what fraction of ionizing photons actually made it out of galaxies and into intergalactic space. The results suggest considerable variation, some galaxies with very high escape fractions approaching 50% or more, others with much lower escape fractions. This variation likely reflects differences in galaxy properties, in their star formation histories, their gas content, their recent merger activity. Understanding what determines the escape fraction is crucial for modelling reionization accurately. There's also the question of whether other sources besides galaxies might have contributed to reionization. Accreting supermassive black holes produce copious ionizing radiation, and if such black holes were abundant enough in the early universe, they might have contributed significantly. But current observations suggest that while black holes existed during reionization, they probably weren't numerous enough to dominate the ionizing photon budget, though they might have played a role in ionizing particularly dense regions. Another possibility involves the death of the very first stars, those purely primordial population 3 stars. If these stars were as massive as theory suggests, their deaths might have been extraordinary events, not just supernovae but perhaps pair instability supernovae, explosions so energetic that they completely destroy the star without leaving a remnant, or even hypothetical quark novae releasing even more energy. These energetic events might have produced ionizing radiation, and possibly other exotic products that affected their surroundings in ways beyond what normal stellar processes do. But we haven't directly observed population 3 stars or their deaths, so these ideas remain speculative, informed by theory but not yet confirmed by observation. Webb might help by finding the signatures of these first stars in the spectra of the earliest galaxies, looking for the chemical abundance patterns that would result from pair instability supernovae, or the effects on surrounding gas from these exotic events. What's becoming clear from Webb's observations is that reionization was not a sudden uniform process, but rather an extended, patchy transformation that played out over hundreds of millions of years, driven primarily by galaxies but potentially influenced by black holes and the exotic deaths of the first stars. Understanding this process helps us understand how the universe transitioned from the Dark Ages to the light-filled cosmos we inhabit, how the conditions were set for the formation of later generations of galaxies, including our own Milky Way. And this connects to a deeper question about why reionization matters, what it tells us about the universe and our place in it. Reionization might seem like an esoteric detail of cosmic history, relevant only to specialists studying the early universe, but it has profound implications for the long-term evolution of the cosmos, and ultimately for the possibility of structures like galaxies, stars, planets, and life itself. When the intergalactic medium was neutral, before reionization, it was cold, with temperatures of perhaps a few tens of degrees Kelvin, barely above absolute zero. Cold neutral hydrogen can collapse efficiently under gravity, fragmenting into clumps that form stars, building up galaxies. But once reionization occurred, the intergalactic medium was heated to temperatures of around 10,000 Kelvin. Typical for ionized hydrogen in equilibrium with the ultraviolet background radiation permeating space. This heating had important consequences for how galaxies formed after reionization. The hot ionized gas has more pressure support, making it harder for gravity to pull it into small galaxies. This effect, called photoheating, essentially shut down the formation of the smallest galaxies, those with masses below a certain threshold where the gravitational potential wells weren't deep enough to hold onto the heated gas. The result is that reionization selected which scales could form galaxies and which couldn't, determining the minimum mass of galaxies that could form after the epoch of reionization. Observations of the galaxy population support this picture. There's a characteristic mass scale below which galaxies become much rarer, consistent with photoheating having prevented their formation. But reionization did more than just set a minimum galaxy mass. It also affected how gas could flow into existing galaxies, changing the fuel supply for star formation. Before reionization, cold neutral gas could stream into galaxies along filaments of the cosmic web, providing fresh fuel for star formation. After reionization, this gas was heated and ionized, making it more difficult for it to cool and fall into galaxies, potentially slowing the rate at which galaxies could grow. This might help explain why galaxies in the later universe form stars relatively inefficiently, converting only a small fraction of their gas into stars each billion years. The combination of stellar and black hole feedback removing gas from galaxies, plus the difficulty of accreting fresh gas from a hot ionized intergalactic medium, means that galaxies self-regulate, unable to form stars as rapidly as gravity alone would allow. In this sense, reionization was a pivotal event in cosmic history, a transition that changed the rules of galaxy formation and evolution, that set the stage for the universe we see today, with its characteristic population of galaxies spanning a range of masses and properties. Without reionization, the universe might have evolved differently, perhaps forming many more small galaxies, or perhaps forming galaxies more efficiently and exhausting their gas supplies more quickly. There's also a connection to the eventual formation of solar systems and planets. The stars that formed after reionization, benefiting from the heavy element enrichment provided by earlier generations of stars that lived and died during the epoch of reionization, had the chemical ingredients necessary to form rocky planets and the complex chemistry needed for life. The first stars, purely primordial objects, couldn't form planets like Earth because there were no heavy elements to make rock and metal. Reionization marks the epoch when the universe transitioned from a state where only the simplest structures could form to one where the full complexity of the cosmos we inhabit became possible. It's a reminder that cosmic history is not just a series of random events, but rather a sequence where earlier events set the conditions for later developments, where the universe builds complexity progressively over time. Understanding reionization also helps us interpret observations of the early universe, because the state of the intergalactic medium affects how we see distant galaxies. Neutral hydrogen absorbs ultraviolet light, particularly light at wavelengths shorter than the Lyman alpha line of hydrogen, creating what's called the Lyman alpha forest in the spectra of distant quasars, a series of absorption features caused by neutral hydrogen clouds along the line of sight. By studying how much absorption occurs at different redshifts, astronomers can map out when reionization occurred, when the universe transitioned from mostly neutral to mostly ionized. Webb's observations are contributing to this effort by finding galaxies and quasars at the highest redshifts, probing the epoch when reionization was ongoing or just completing, providing the data needed to refine our understanding of this cosmic transformation. And as we understand reionization better, We also gain insights into the broader story of how the universe evolved from simplicity to complexity. From a smooth, nearly uniform state just after the Big Bang, to the richly structured cosmos we inhabit, full of galaxies, stars, planets, and ultimately life and consciousness contemplating its own origins. This progression from simplicity to complexity, from uniform to structured, is one of the great themes of cosmic history, and it raises profound questions about why the universe is the way it is, why the fundamental constants and laws of physics have the values they do. Values that allow for stars and galaxies and planets and life. The fact that Webb can observe galaxies form in just a few 100 million years after the Big Bang, that we can trace cosmic history from the initial fireball to the present day, that the universe has been stable and structured enough for 13.8 billion years to allow complexity to develop. All of this rests on what seems like an extraordinary series of fortunate circumstances involving the fundamental properties of nature itself, the laws of physics, the values of fundamental constants like the strength of gravity or the mass of the electron or the charge of the proton appear to be fine-tuned, set to values that allow for a rich, complex, long-lived universe. Change any of these constants by even modest amounts, and the universe becomes inhospitable to complexity. Unable to form stars or galaxies or any of the structures that make the cosmos interesting. If gravity were slightly stronger, the universe might have collapsed back on itself shortly after the Big Bang, never living long enough for stars to form. If gravity was slightly weaker, matter might never have clumped into galaxies, remaining forever diffuse and featureless. If the strong nuclear force binding protons and neutrons into atomic nuclei was slightly different, stars might not be able to synthesize the elements needed for planets and life. The carbon atom, essential to all life we know, exists because of a remarkable resonance in how helium nuclei can fuse to form carbon in the cores of stars, a resonance that depends on the precise masses of particles and the strengths of forces. Change these values slightly, and carbon becomes rare or impossible to form, eliminating the possibility of carbon-based chemistry and life. These observations have led to considerable debate about what they mean, whether they point towards some deeper explanation or are simply brute facts about reality that we must accept without deeper understanding. Some physicists suggest that the apparent fine-tuning points toward a multiverse, a vast ensemble of universes with different physical constants, most of them sterile and lifeless, but a few, including ours, having the right conditions for complexity. In a multiverse, there's no mystery about why our universe has the right properties for life. We exist in one of the rare universes where those properties allow observers to evolve, while the vast majority of universes remain forever barren and unobserved. This explanation, called the anthropic principle, argues that the fine-tuning we observe is a selection effect. We can only find ourselves in a universe capable of producing observers. Others find this explanation unsatisfying, preferring to think that there might be a deeper theory, some underlying framework that explains why the constants have the values they do, that derives them from more fundamental principles rather than accepting them as arbitrary inputs. String theory and other approaches to quantum gravity have explored this possibility, suggesting that what we call fundamental constants might actually be determined by the geometry and topology of extra dimensions, or by the vacuum state of quantum fields. But these are speculative ideas, not yet testable with current technology, and it's unclear whether they'll ever be testable directly. We might be at a fundamental limit of what we can know through observation, able to measure the constants that govern our universe, but unable to explain why they have the values they do, because those explanations lie beyond what we can observe in principle. There's something both humbling and awe-inspiring about this possibility, the idea that we might have reached the edge of what can be known through science, that the universe might contain deeper truths forever beyond our reach. Yet even if that's the case, what we can know is extraordinary. The ability to trace cosmic history back to moments after the beginning, to understand how stars and galaxies form, to see light that's been travelling for billions of years carrying information about the early universe. Webb's observations fit into this larger context as part of humanity's ongoing effort to understand the cosmos, to push back the boundaries of ignorance, to see farther and deeper than ever before. Each new observation, each distant galaxy found, each puzzle revealed is a step forward in this ancient quest. One that stretches back through the history of astronomy to the first humans who looked up at the night sky and wondered what they were seeing. The fine-tuning question also connects to a more immediate consideration about our place in the universe, about whether we're alone or whether the cosmos might harbour other instances of complexity, other observers contemplating their own origins. The fact that our universe allows for complexity, for chemistry and evolution and consciousness, raises the question of whether these things are unique to Earth or might be common throughout the cosmos. Current observations don't provide a clear answer. We've discovered thousands of planets orbiting other stars, many of them potentially Earth-like, orbiting in their stars' habitable zones, where liquid water could exist on their surfaces. But we haven't yet detected definitive signs of life beyond Earth, haven't found the biosignatures in exoplanet atmospheres that would indicate biology, haven't received signals from technological civilizations. The question of whether we're alone remains open, one of the great unknowns of our time, and interestingly, understanding the early universe and how galaxies formed connects to this question, because it tells us about the history of star formation throughout cosmic time, about when and where the conditions for planets and life became possible. The peak of star formation in the universe occurred when the universe was about 3 billion years old, earlier than Earth formed, meaning there are likely star systems and planets billions of years older than our solar system, places where life, if it arose, has had far longer to evolve and develop than on Earth. Yet we see no evidence for galaxy-spanning civilizations, no signs of astroengineering projects or large-scale modifications of the cosmos. This absence might mean life is rare, or technological civilization is rare, or advanced civilizations don't engage in visible astroengineering. Or they exist but we haven't recognised their signatures, or any number of other possibilities. The question remains open, and Webb's observations, by showing us more of the universe's history and structure, contribute to the context in which we consider it. And perhaps this uncertainty, this not knowing, is part of what makes the exploration meaningful. The sense that we're genuinely discovering things rather than just confirming what we already knew, that the universe still has the power to surprise us, to challenge our assumptions, to reveal truths we hadn't imagined. One of the tools that has made some of Webb's deepest observations possible is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity where massive objects bend space itself, causing light to follow curved paths and creating natural magnification that allows us to see farther into the universe than would otherwise be possible. When light from a distant galaxy passes near a massive galaxy cluster lying between us and the distant galaxy, the cluster's gravity bends the light's path, focusing it like a lens. If the alignment is right, this can magnify the distant galaxy, making it appear brighter and larger than it would otherwise, sometimes magnifying it by factors of 10 or even 100, bringing objects into view that would be too faint to see without the magnification. Webb has taken advantage of this natural magnification to observe some of the most distant galaxies ever seen, pointing at massive galaxy clusters that act as gravitational lenses and studying the distorted, magnified images of galaxies behind them. These observations have revealed galaxies that would be completely invisible to Webb without the lensing magnification, pushing our view of the universe back to even earlier times. The lensing effect depends on the mass distribution of the lensing cluster, and by studying how background galaxies are distorted and magnified, astronomers can actually map out the distribution of dark matter in the cluster, seeing where the invisible mass lies by how it affects the light passing nearby. This technique has provided some of the best evidence we have for dark matter's existence, and has helped constrain its properties. Some of the lensed galaxies appear as multiple images, the light taking different paths around the cluster and arriving at our telescopes from different directions, creating duplicates of the same galaxy at different positions in the image. By measuring the positions and brightnesses of these multiple images, astronomers can refine their models of the cluster's mass distribution and test our understanding of general relativity and strong gravitational fields. This disagreement, called the Hubble tension, is another place where observations don't perfectly match expectations, where different measurements of the same quantity give slightly different answers. Like Webb's observations of unexpectedly massive early galaxies, the Hubble tension might indicate new physics, or it might reflect unrecognized systematic errors in one or both measurement methods. The scientific community continues to investigate, refining measurements and exploring possible explanations. What's clear is that the universe continues to challenge our understanding in subtle ways, pushing us to be more careful, more thorough, more creative in how we interpret observations and build models. And perhaps that's as it should be, the universe maintaining a slight air of mystery even as we learn more about it, always holding back a few surprises to keep the exploration interesting. As we reach the midpoint of our journey through Webb's discoveries and their implications, it's worth pausing to acknowledge how much we still don't know, how many questions remain open despite decades of observations and theoretical work, how the universe continues to guard many of its secrets even as it reveals others. We don't know what dark matter is, what particles comprise this invisible substance that makes up most of the matter in the universe. We've detected its gravitational effects, seen how it bends light and shapes the cosmic web, but we haven't directly observed a dark matter particle, haven't measured its properties beyond its gravitational influence. It might be a new type of particle predicted by extensions of the standard model of particle physics, or it might be something more exotic, perhaps black holes formed in the early universe, or some other entity we haven't yet imagined. We don't know what dark energy is, the mysterious force causing the universe's expansion to accelerate, pushing galaxies apart faster as time goes on. The simplest explanation is Einstein's cosmological constant, a property of space itself that exerts a constant negative pressure, but we don't understand why it has the value it does, why it's so small compared to what quantum field theory seems to predict. Alternative explanations involving new scalar fields or modifications to gravity remain possibilities, but we lack the observations needed to distinguish between them. We don't know exactly when and how the first stars formed, what their properties were, whether they formed in isolation or in clusters, how they affected their surroundings. Webb is helping to constrain these questions by observing the epoch when the first stars should have existed, but directly seeing individual first stars remains beyond even Webb's capabilities. We're seeing the integrated light from early galaxies containing thousands or millions of stars, not the individual first stars themselves. We don't know how supermassive black holes formed, whether they grew from stellar remnants, or formed through direct collapse, or emerged from primordial density fluctuations. We're observing the consequences of their existence, seeing their effects on galaxies and the light from material accreting onto them. But the formation mechanism remains uncertain, one of the major unsolved problems in astrophysics. We don't know whether our theories of the very early universe are correct, whether inflation actually occurred, what drove it if it did, whether our understanding of physics breaks down at the extreme energies and densities present in the first moments after the Big Bang. These questions lie at the boundary between observational cosmology and theoretical physics, where our theories are least constrained by data and most speculative. We don't know whether the universe is infinite or finite, whether space curves back on itself or extends forever, whether there's an edge or whether it goes on without limit. The observable universe is finite, limited by the distance light has travelled since the Big Bang, But beyond that horizon might lie more universe, or something else entirely, or perhaps the question itself doesn't have meaning in the way we frame it. We don't know whether we're alone in the universe, whether life arose elsewhere among the hundreds of billions of galaxies, each containing hundreds of billions of stars, whether intelligence and technology are common or rare, whether civilizations tend to be long-lived or self-destructive. These questions move beyond physics into biology and sociology, but they're part of the larger question about our place in the cosmos, about whether the universe is fundamentally hospitable to complexity and consciousness, or whether we're an extraordinary accident. These philosophical questions sit alongside the scientific ones, equally valid, equally important, and perhaps equally unanswerable with current methods. But asking them, contemplating them, holding space for mystery alongside knowledge, seems essential to a full engagement with reality, to being thoughtful observers of the universe rather than just passive inhabitants. As we move forward into the second half of our exploration, we'll look more closely at specific discoveries Webb has made, at individual galaxies and phenomena that exemplify the themes we've been discussing. And we'll also begin the gentle turn toward contemplation and synthesis that will carry us through to our conclusion. There's much still to explore, but we'll take our time, let the ideas settle, allow space for wonder alongside understanding, let that thought rest as we continue. Among the thousands of galaxies Webb has observed, a few have captured particular attention, becoming exemplars of what the telescope can reveal about the early universe. Individual systems studied in detail and given names that astronomers and the public have come to recognize. These galaxies represent different aspects of early cosmic history, each one telling its own story about how structure formed in the universe's youth. GLASS-z13, one of the earliest galaxies confirmed through spectroscopy, existed when the universe was approximately 350 million years old, making it one of the most distant objects ever observed. This galaxy appears as a small reddish smudge in Webb's images, unremarkable at first glance. But spectroscopic analysis reveals it contains stars actively forming, building up mass in the early universe at a rate that suggests a dynamic, rapidly evolving system. The spectrum shows emission lines from ionized oxygen and hydrogen, indicating the presence of young hot stars whose ultraviolet radiation ionizes the surrounding gas. The measured redshift places this galaxy at a time when reionization was likely still ongoing, when the universe was transitioning from neutral to ionized, making GLASS-z12 one of the sources contributing to that cosmic transformation. Another notable galaxy, Maisie's Galaxy, named after the daughter of one of the astronomers who discovered it, exists at a similar epoch and shows evidence for an older stellar population alongside ongoing star formation. This suggests the galaxy had already been forming stars for tens or even hundreds of millions of years by the time we're seeing it, implying star formation began even earlier than the observed epoch. The name itself is touching, a personal connection between an astronomer and their work, a reminder that behind all the technical language and sophisticated analysis are human beings driven by curiosity and wonder, people with families and lives who happen to spend their days studying the most distant objects in the universe. These personal names make the galaxies feel more real, more individual, less like catalogue numbers and more like places, worlds with their own histories waiting to be understood. HD1, another early galaxy candidate, appeared in Hubble data and was followed up with Webb, potentially existing just 300 million years after the Big Bang. This galaxy is interesting because it's very bright, suggesting either an extremely high star formation rate or possibly the presence of an accreting supermassive black hole contributing to the luminosity. The uncertainty highlights how difficult it can be to interpret observations of these distant systems, how multiple explanations might fit the data. Some galaxies show evidence for dust even at these early epochs. Tiny solid particles that form from heavy elements in stellar atmospheres and supernova ejections. The presence of dust so early suggests rapid chemical enrichment, multiple generations of stars living and dying within the first few 100 million years, processing primordial gas into heavier elements and producing enough of those elements to form significant amounts of dust. Others show surprisingly regular morphologies. Disk-like structures suggesting the gas has settled into rotation around the galaxy's centre, a level of dynamical organisation that seems premature for such young systems. These observations challenge theorists to explain how galaxies could become so organised so quickly, how the chaotic, turbulent conditions of the early universe could give way to settled, rotating structures in such short timescales. There are also galaxies showing signs of mergers, multiple clumps of stars apparently in the process of coming together to form larger systems. These observations support the hierarchical formation scenario where galaxies grow through mergers, smaller systems combining to form larger ones, building mass through accretion and collision rather than forming all at once. The diversity of these early galaxies is itself remarkable. The fact that even in the first few 100 million years, galaxies weren't all the same but showed variety in their properties, their star formation rates, their morphologies, their chemical compositions. This diversity suggests that whatever processes shaped early galaxies allowed for multiple pathways, multiple ways for structure to form and evolve. Each of these galaxies, these individual systems with names and stories, represents a unique window into the early universe, a specific example of how matter organised itself in those first cosmic moments. By studying them in detail, by measuring their spectra and morphologies and properties, astronomers build up a statistical picture of the early galaxy population, constraining models and refining our understanding of cosmic history. And there's something deeply moving about this work, the dedication required to study these faint, distant smudges, to spend hours collecting photons that have been travelling for billions of years, to carefully analyse spectra and measure redshifts and calculate masses, all in service of understanding objects so distant that they existed when the universe was young, light, from a time closer to the beginning than to the present. The people doing this work are exploring territory never before seen, pushing human knowledge into new realms, and they do it with a combination of technical sophistication and genuine wonder that's inspiring. They're cartographers of cosmic history, mapping out when galaxies formed, how they evolved, what the universe was like in its infancy, contributing to a story that belongs to all of us. A story about where we came from and what we're part of. One of Webb's most powerful capabilities is its ability to conduct ultra-deep observations, pointing at a single patch of sky for extended periods, accumulating photons hour after hour, day after day, revealing objects so faint they would be completely invisible in shorter exposures. These deep-field observations follow a tradition established by Hubble, which revolutionised our understanding of the distant universe with its deep-field and ultra-deep-field images. The Hubble Deep Field, observed in 1995, pointed at a seemingly empty patch of sky in Ursa Major for 10 consecutive days, gathering light from the faintest objects possible. The resulting image revealed thousands of galaxies where none had been visible before, galaxies at various distances and redshifts, a three-dimensional cross-section through cosmic time showing how galaxies evolved and what the universe looked like at different epochs. Webb's deep fields build on this legacy, going deeper than Hubble could, seeing farther back in time, revealing galaxies from epochs that Hubble could barely glimpse. The JWST Advanced Deep Extragalactic Survey, or JADES, conducted some of these observations, studying regions that Hubble had already observed deeply, but pushing to even fainter limits with Webb's larger mirror and infrared sensitivity. When all the exposures are combined, what emerges is an image of extraordinary depth, showing objects millions or billions of times fainter than what the human eye can see, revealing a universe invisible to us without technology, but always present, always there, waiting to be observed. These images are both scientific data and works of art, beautiful in their complexity, in the tapestry of galaxies they reveal, in the sense they convey of an intricate universe full of structure across all scales. Looking at a deep field image, one can't help but feel a sense of scale, a recognition of how vast the universe is, how many galaxies exist, how many stars, how many potential planets. If each galaxy in the deep field contains 100 billion stars, and there are thousands of galaxies in the image, the total number of stars becomes almost incomprehensible. A number so large it loses meaning, becomes an abstraction. Yet each of those stars is a sun, potentially with its own family of planets, its own story of formation and evolution, its own place in cosmic history. The deep fields remind us that what we see is just a tiny sample, one small patch of sky, and if we could observe the entire sky with the same depth, we'd find similar richness everywhere. Billions of galaxies, each containing billions of stars, a cosmos so vast and complex that it defies complete comprehension. Some people find this overwhelming, the sheer scale of the universe diminishing, making human concerns seem trivial by comparison. But there's another way to see it, a recognition that we're part of this vast cosmos, that our atoms were forged in stars, that our existence depends on the universe being the way it is, large and old and complex enough for complexity to emerge, for life to arise, for consciousness to develop. The deep fields show us where we came from in a cosmic sense. The galaxies forming and evolving over billions of years, building up the heavy elements, creating the conditions that eventually allowed for solar systems like ours, planets like Earth, life like us. We're made of star stuff, as Carl Sagan famously said, and the deep fields show the stars in their vast multitudes, the furnaces where our constituent atoms were created. There's also something meditative about contemplating these images, letting your eyes wander across the field, picking out individual galaxies, thinking about how far their light has travelled, how long ago it was emitted, what the universe was like when those photons began their journey. Time and space become tangible in a way they rarely do, compressed into a single image that spans billions of years and billions of light years simultaneously. The success of the James Webb Space Telescope represents a convergence of preparation and fortune, decades of planning and engineering meeting circumstances that could easily have gone differently, turning the project from a triumph into a cautionary tale. The fact that Webb worked, that every deployment step succeeded, that the telescope is performing better than its design specifications, is both a testament to human ingenuity and a reminder of how narrow the margin can be between success and failure. The telescope's journey to its observing location, the second Lagrange point, or L2, required launching on an Ariane 5 rocket, folding the entire observatory into a space small enough to fit inside the rocket's fairing, then successfully deploying in a sequence of more than 300 critical steps, any one of which could have failed and ended the mission. The deployment began shortly after launch and continued over the course of 2 weeks as the spacecraft travelled toward L2. The sun shield, 5 layers of thin material each the size of a tennis court, had to unfold and separate precisely, creating the thermal barrier that keeps the telescope cold enough to observe in the infrared. The primary mirror segments, 18 hexagons that together form the collecting area, had to deploy and align to within nanometers. The secondary mirror, instruments, every component had to work perfectly in the vacuum and radiation of space, conditions that can't be fully replicated in testing on Earth. This combination of prepared instrument and prepared observers created conditions for rapid progress, the pace of discovery accelerating as each new observation raised questions that could be addressed with additional observations. A virtuous cycle of observation and interpretation that continues to produce results. There's a lesson here about the value of investing in basic science, in building capabilities like Webb without knowing exactly what they'll find, trusting that if we create tools powerful enough to see farther and deeper than before, they'll reveal things worth seeing. The history of astronomy supports this trust. Every time we've built a more powerful telescope or detector, We've discovered phenomena we didn't expect, learned things we couldn't have predicted. Webb is following this pattern, finding galaxies that challenge our models, black holes that shouldn't exist yet, structures that formed earlier than expected. These discoveries aren't the result of looking for something specific and finding it. They're the result of looking at the universe with new eyes and seeing what's actually there, which often differs from what we expected or predicted. The willingness to be surprised, to let observations guide understanding rather than forcing observations to fit preconceptions, is essential to good science. It requires a certain humility, an acknowledgement that our theories are provisional, our models incomplete, our understanding limited. But it also enables progress, allowing new observations to reshape understanding, to point toward better theories and more complete models. As Webb continues operating, as more data accumulates and more observations are analysed, this process will continue, theory and observation pushing each other forward, each discovery raising new questions that motivate further observations, each observation constraining theories and suggesting new directions for theoretical work. The specific discoveries might be unpredictable, but the process itself is reliable, the scientific method proving effective across centuries of application. There's something deeply strange about the fact that when we look at distant galaxies, we're seeing the past, observing those galaxies not as they are now, but as they were when their light began its journey toward us. The light from a galaxy, 10 billion light-years away, was emitted 10 billion years ago, when the universe was less than a third its current age, showing us that galaxy in its youth, rather than its present state. This means we can never see the current state of distant objects, can never observe the universe as it exists now across all its vast extent. We're limited to seeing a light cone, the set of events whose light has had time to reach us since the universe began, and everything beyond that light cone is, in principle, forever unobservable, not because of any limitation in our technology, but because of the fundamental structure of space-time and the finite speed of light. The most distant galaxies Webb observes existed when the universe was just a few 100 million years old, meaning we're seeing them as they were more than 13 billion years ago. What are these galaxies like now, today? We can't know through direct observation, but we can model their likely evolution, running simulations forward in time to predict how they should have grown and changed over the intervening billions of years. Most likely, those early galaxies have merged with other galaxies, grown substantially through accretion and mergers, building up mass and evolving into large systems, perhaps comparable to the Milky Way or Andromeda. The individual stars that existed in those early galaxies have long since died. Their mass returned to the interstellar medium or locked in remnants like white dwarfs, neutron stars or black holes. New generations of stars have formed, enriched by the deaths of earlier generations, building up chemical complexity over cosmic time. The light travel time also means that different parts of the universe as we observe them exist at different cosmic times. When we look at the sky, we're seeing a collage of different epochs, nearby objects as they were recently, more distant objects as they were progressively longer ago, the most distant objects as they were in the universe's youth. Space and time become mixed in observation, distance translating to age. Every direction a journey backward in time. This is why cosmology is fundamentally a historical science, studying the evolution of the universe through time by observing objects at different distances and thus different epochs. We can't run controlled experiments on the universe, can't manipulate it to test hypotheses the way we might in a laboratory. Instead, we observe what exists, what has happened, using observations to constrain models and test theories against the reality of cosmic history. There's also a philosophical dimension to this time delay, a recognition that the universe we observe is not the universe as it currently exists, but rather the universe as it was across a range of past times. In some sense, the now of the universe as a whole is not directly accessible to us. We're always seeing the past, and the present of distant regions is forever beyond our observation. moving into the future faster than light can bring us information about it. This creates a kind of cosmic horizon, not just the event horizon of black holes where nothing can escape, but an observational horizon beyond which we cannot see. Defined not by distance alone, but by the combination of distance and the age of the universe. As the universe ages and light has more time to travel, this horizon expands, bringing more of the universe into potential observability. But there are regions that will forever remain beyond what we can see, their light not yet having had time to reach us. In an accelerating universe dominated by dark energy, this horizon becomes more complicated because distant regions are receding from us faster than light can travel through the expanding space between us, meaning light from events occurring there now will never reach us, will be carried away by expansion faster than it can approach. This creates a future where the observable universe, while currently growing, will eventually begin to shrink as more and more distant objects cross this cosmic horizon and disappear from view. These are profound thoughts, touching on the limits of what we can know, the fundamental constraints that physics places on observation and understanding. But they're also part of what makes cosmology meaningful, the recognition that we're exploring not just space but time, not just asking how the universe is, but how it came to be, how it changes, what it will become. One of the most valuable lessons from Webb's discoveries, from the puzzles and questions they've raised, is the importance of holding our knowledge lightly, recognizing that what we think we know might be incomplete or wrong, that the universe has surprised us before and will likely surprise us again, that certainty is often premature and humility is almost always warranted. The galaxies that Webb has found that don't quite match our models remind us that models are simplified representations of reality, useful tools for organizing our thinking and making predictions, but not perfect descriptions of how nature actually works. Every model makes assumptions, simplifies complex processes, ignores factors deemed less important. And sometimes those simplifications or ignored factors turn out to matter more than we thought. This doesn't mean our models are useless, or that we don't know anything. Lambda-CDM successfully explains a vast range of observations, from the cosmic microwave background to the large-scale distribution of galaxies to the expansion history of the universe. But it might be incomplete, might need refinement or extension to fully capture what Webb is observing in the early universe. Recognizing this possibility, being open to revising our understanding when observations demand it, is essential to how science progresses. The wonder doesn't contradict the analysis, it complements it, providing emotional engagement with the subject matter that sustains the work of studying it in detail. Scientists are not purely rational beings unmoved by the beauty of their subjects. They're humans who chose their fields, often because they found them fascinating, beautiful, worthy of a life's dedication. Looking at Webb's images, at galaxies scattered across space and time, it's hard not to feel something. Whether it's awe at the scale, curiosity about what those galaxies are like, satisfaction at understanding how they form, or peace in contemplating the vastness of cosmic history. These emotional responses are valid, valuable, part of what makes the exploration meaningful. There's also a kind of humility that comes from confronting the universe's scale and age, a recognition of how small we are in space and time, how brief our lives are compared to cosmic timescales, how recent our species is in the history of the universe. Humans have existed for perhaps a few 100,000 years, civilization for perhaps 10,000, modern science for a few centuries. Against the 13.8 billion year history of the universe, we're incredibly recent, a tiny blip. Yet we can understand cosmic history, can trace it back to moments after the beginning, can observe galaxies from the universe's youth. That capability, that ability to comprehend scales vastly larger than ourselves, is remarkable, suggesting that intelligence and consciousness, however recent and small scale they might be cosmically, give us a kind of reach that transcends our physical limitations. We're part of the universe understanding itself, pieces of the cosmos that have organised themselves into patterns capable of contemplating the whole. That's a profound and beautiful thing, worthy of appreciation alongside all the technical analysis and careful measurement that characterise modern astronomy. As we move into our final act, we'll begin turning more fully toward contemplation and synthesis, bringing together the threads we've been following, considering what it all means, allowing the journey to resolve into something peaceful and complete. There's still more to explore, but the explorat becomes gentler, more meditative, preparing for rest. Let that thought settle as we continue. Throughout our exploration of Webb's discoveries, we've been focused on what we can observe, the galaxies and phenomena visible to our instruments, the light that has reached us carrying information about distant places and times. But there's another dimension to cosmology, the recognition that what we can observe is only a small fraction of what exists, and that most of the universe lies forever beyond our observational horizon, unknowable through direct observation, but perhaps inferable through reason and imagination. The observable universe, the region from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years, accounting for the expansion of space during the light's journey. But there's no reason to think the universe ends at this horizon. Space almost certainly continues beyond what we can see, containing more galaxies, more structure, more cosmic history unfolding in regions we can never observe. How far does the universe extend beyond the observable horizon? We don't know. It might be much larger than the observable region, perhaps infinite, extending forever in all directions. Or it might curve back on itself, be finite but unbounded like the surface of a sphere, where travelling far enough in one direction brings you back to where you started. Current observations of the cosmic microwave background constrain how much the universe can curve, suggesting that if it's finite, it's at least much larger than the observable region. Perhaps hundreds of times larger or more. But exact measurements are difficult, because any curvature shows up as very subtle effects in the microwave background pattern, and measurement uncertainties prevent definitive conclusions. The topology of the universe is another unknown, how space is connected on the larger scales. A flat, infinite universe is the simplest topology, but other possibilities exist. Multiply connected spaces where different regions are linked in non-obvious ways, creating complex topologies where the universe might be finite but still unbounded, with no edge. These questions about the overall structure and extent of the universe might seem academic, disconnected from the practical business of observing galaxies and measuring their properties. But they touch on deep questions about the nature of existence, about what lies beyond what we can see, about whether the universe is fundamentally comprehensible, or contains aspects forever beyond human understanding. If the universe is infinite, it contains infinitely many galaxies, infinitely many stars, infinitely many planets. In an infinite universe with finite age, every possible arrangement of matter that doesn't violate physical laws should occur infinitely many times, including exact duplicates of Earth, copies of every person who has ever lived, every event that has ever happened recurring infinitely many times throughout infinite space. This is a strange and unsettling thought. The idea that somewhere infinitely far away there might be another you reading these same words, identical in every detail, with other copies differing in small or large ways, exploring all possible variations of the human story. These duplicates would be causally disconnected from us, unable to interact or communicate due to the speed of light limit and the expansion of space, but they would exist nonetheless if the universe is truly infinite. If the universe is finite but larger than the observable region, these duplicates might still exist but in finite numbers, and the overall structure of space would matter, whether it curves back on itself or has some more complex topology. These possibilities have been explored in theoretical cosmology, but observations haven't yet distinguished definitively between them. There's also the question of the multiverse, the possibility that our universe is one of many, each with potentially different physical constants or laws, existing in some larger structure that we can't observe directly. The multiverse idea arises naturally from some theoretical frameworks, particularly eternal inflation, which suggests that the inflationary expansion that occurred in the early universe might be ongoing in other regions, creating bubble universes with different properties. If the multiverse exists, it would resolve some of the fine-tuning questions we discussed earlier, explaining why our universe has the right properties for complexity by anthropic selection. We exist in one of the rare universes with suitable properties because those are the only universes that can produce observers. But the multiverse remains speculative, difficult or impossible to test observationally, because other universes, if they exist, are causally disconnected from ours. These ideas about what lies beyond observation, about the overall structure of reality, are exercises in imagination constrained by mathematics and physical law. We can't observe other universes or regions of space beyond our horizon, but we can reason about what they might be like, using our understanding of physics to explore possibilities. This kind of reasoning has value even without direct observational confirmation, because it expands our conception of what might exist, challenges us to think beyond immediate experience, exercises the imagination in ways that can lead to new insights and ideas. Some of the greatest advances in physics came from theoretical work exploring possibilities that weren't yet observable, predictions later confirmed by observations. And there's something profound about contemplating the unobservable, about recognizing that reality likely extends far beyond what we can directly access, that our observations show us only a fraction of what exists. It's humbling, reminding us that our perspective is limited, our knowledge incomplete, our access to truth constrained by fundamental limits of observation. But it's also inspiring, suggesting that the universe is far richer and more complex than what we can directly see, that reality has depths we're only beginning to explore, that the quest for understanding can continue indefinitely, because there will always be more to learn, more to discover, more to contemplate. We've spent much of our journey looking backward in time, observing galaxies from the early universe, contemplating what the cosmos was like billions of years ago. But there's another temporal direction to consider, looking forward into the deep future, thinking about what will happen to the universe over coming billions and trillions of years as cosmic evolution continues. The current understanding suggests the universe will expand forever, driven by dark energy causing the expansion to accelerate, galaxies beyond our local group receding faster and faster until they cross the cosmic horizon and disappear from view. Over hundreds of billions of years, the sky as seen from our galaxy will become increasingly empty, more and more distant galaxies redshifting beyond detectability, leaving only the gravitationally bound local group of galaxies visible. Eventually, after many billions of years, the Milky Way will merge with Andromeda, the two galaxies colliding and combining to form a single larger elliptical galaxy. This merger is inevitable. The mutual gravitational attraction overcoming the expansion of space because the galaxies are close enough to be bound. The process will take billions of years, the two galaxies passing through each other initially, then falling back together, gradually merging through multiple encounters. Star formation will continue for a long time, but not forever. The universe has a finite supply of hydrogen to convert into stars, and eventually, after many trillions of years, that supply will be exhausted. Stars currently forming will live out their lives and die, and no new stars will form to replace them. The longest-lived stars, small red dwarfs, can live for trillions of years, but eventually they too will exhaust their fuel and die. After star formation ceases, the universe will gradually cool and darken, with only stellar remnants remaining, white dwarfs, neutron stars, and black holes. These remnants will slowly cool, radiating away their heat over incredibly long timescales, approaching but never quite reaching absolute zero. White dwarfs will cool to black dwarfs, dark cinders of degenerate matter no longer emitting light. Even these remnants aren't forever. On timescales almost incomprehensibly long, perhaps 10 to the 100 years or more, protons might decay, their matter converting to radiation and leaving behind nothing but photons and the lightest particles. This process is speculative, not yet observed, but predicted by some extensions of the standard model of particle physics. Black holes, which might seem permanent, actually evaporate through Hawking radiation, a quantum process where particles and antiparticles form near the event horizon, with one particle escaping as radiation while the other falls in. This process is incredibly slow for stellar mass black holes, taking far longer than the current age of the universe, but for supermassive black holes like those in galaxy centers, the evaporation time is even longer, perhaps 10 to the 100 years or more. After black holes evaporate, only radiation remains, a universe dark and empty, with nothing but photons and light particles diluted by endless expansion, approaching a state of maximum entropy, absolute uniformity, no remaining structure or complexity. This is the heat death scenario, the far future state where nothing interesting can happen, because there's no free energy, no gradients to drive processes, just uniform radiation expanding into infinite emptiness. These timescales are so vast they lose meaning, numbers so large they can barely be contemplated. The current age of the universe, 13.8 billion years, is nothing compared to the trillions of years until star formation ceases, which is nothing compared to the incomprehensible timescales for proton decay or black hole evaporation. Yet physics suggests this is the ultimate fate, the universe's long slow decline from order to disorder, from complexity to simplicity. It's a melancholy vision in some ways, the idea that everything we see, all the structure and complexity, all the galaxies and stars and planets, are temporary phenomena, destined to eventually fade into uniform emptiness. But there's also a kind of peace in it, the recognition that the universe follows its own course according to physical law, that cosmic evolution will continue long after we're gone, playing out across timescales that make human history seem infinitesimal. And perhaps that long view provides perspective on our own existence, the recognition that we live in a special time cosmically, when stars still shine and galaxies still form, when the universe is rich with structure and complexity, when consciousness can arise and contemplate existence. The far future will be empty and dark, but we're here now, in the time when things are interesting, when the universe is full of light and motion and change. Our existence, our observations, our understanding, all of it happens during this brief window, cosmically speaking, when the universe is neither too young for complexity to have developed, nor too old for structure to persist. We're living in what might be called the universe's middle age, after the turbulent youth of the early universe, but long before the empty senescence of the far future. This perspective doesn't make our lives more or less meaningful in some objective sense, but it provides context, a framework for understanding our place in cosmic history. We're observers of the universe during its most interesting phase, participants in the brief moment when matter is organized into complex structures capable of understanding themselves before entropy wins and everything dissolves into uniform simplicity. And in that brief moment, we can do what we're doing now, observe the universe, understand its history, contemplate its future, create meaning through our consciousness and our understanding. That seems like a worthwhile way to spend the time we have, to use our brief window of existence to explore and understand and appreciate the cosmos that gave rise to us. After our long journey through cosmic history, through billions of years and billions of light years, through puzzles about early galaxies and contemplations of the far future, it feels right to return our attention to Earth, to this small planet orbiting an ordinary star in an unremarkable region of an average galaxy, the only place in all of that vast cosmos where we know life exists. Earth appears in Webb's images not as a subject of study. Webb looks outward to distant galaxies rather than inward at our solar system, but it could be there. A tiny point of reflected light if Webb were pointed toward the inner solar system, indistinguishable from countless other faint points, except that it's the one that matters to us, the one we call home. Carl Sagan famously reflected on an image of Earth taken by Voyager 1 from the outer solar system, showing our planet as a pale blue dot, barely visible, a tiny pixel in the vastness of space. He wrote about how that perspective shows the folly of human conflicts, of wars and disputes over patches of ground on that tiny dot, how it reminds us that everyone we know, everyone who has ever lived out their lives on that small stage. That perspective, looking at Earth from a cosmic distance, can inspire both humility and care. Humility at our smallness in cosmic terms, care for the only home we have and the only place where all of human experience has occurred. All of history, all of art and music and literature, all of science and exploration. All of love and suffering and joy, all of it happened on this small planet, this thin film of life on the surface of a rocky world. Webb's observations, while focused on the distant universe, ultimately connect back to Earth and life because they help us understand the cosmic context in which our planet exists. The processes that led to its formation, the elements that make it up, the conditions that made life possible. The galaxies Webb observes were forming the stars that created the heavy elements Earth is made of, processing primordial hydrogen and helium into carbon and oxygen and iron, and all the other elements essential to rocky planets and biology. Understanding cosmic history helps us appreciate how special and contingent our existence is, how many things had to go right for Earth to exist, and for life to arise and persist, and eventually produce consciousness capable of contemplating its own origins. The universe didn't have to be this way, could have been different in countless ways, most of which wouldn't have allowed for planets or life or observers. Yet here we are, products of 13.8 billion years of cosmic evolution, made of stardust, conscious pieces of the universe pondering our own existence. That's remarkable, worthy of wonder, a fact that never quite loses its power to inspire even as we become familiar with the details of cosmic history. Living on Earth in the era of Webb, we have access to knowledge that previous generations could only dream of. The ability to observe the universe when it was young, to see galaxies forming 13 billion years ago, to trace cosmic history from the Big Bang to the present. This knowledge is a gift, the product of centuries of scientific work, of people dedicating their lives to building telescopes and analysing data and developing theories. We can choose what to do with this knowledge, how to let it inform our lives and our perspective. For some, it inspires dedication to further scientific exploration, careers spent pushing the boundaries of understanding even further. For others, it provides context and perspective, a framework for thinking about existence and meaning that enriches life without necessarily directing it towards science. There's no single right response to cosmic knowledge, no particular action it demands. But perhaps it suggests a kind of responsibility to care for Earth and each other, to appreciate the extraordinary improbability of our existence, to use our brief time wisely, to contribute something positive to the human story that's been unfolding on this small planet. The problems we face on Earth, climate change, conflict, inequality, all the challenges that occupy our attention daily, don't disappear when we contemplate the cosmos. If anything, the cosmic perspective makes them seem more urgent, reminding us that we have only this one planet, this one home, and we need to take care of it and each other. But the cosmic perspective also provides hope, the recognition that we're capable of remarkable things, that humanity can work together to build instruments like Webb, to explore the universe, to develop knowledge and understanding, to create beauty and meaning. If we can do that, perhaps we can also address our earthly challenges, can find ways to live sustainably and peacefully. can build a future worthy of our cosmic heritage. And maybe that's where our journey through Webb's discoveries ultimately leads, back to Earth and to ourselves, to the recognition that we're part of something vast and ancient and ongoing, that we have both the knowledge and the responsibility to choose wisely how we live and what we do with the time we have. The galaxies Webb observes will continue existing long after we're gone, following their own evolutionary paths according to physical law. The universe will unfold according to its nature, whether we understand it or not. But understanding matters, creates meaning, connects us to the cosmos in ways that enrich experience and provide perspective. And with that understanding, that connection, that cosmic perspective, informing our earthly lives, perhaps we can find both humility and inspiration, both peace in accepting what we can't control and motivation to work on what we can, both wonder at the universe's vast scale and appreciation for the small, beautiful moments that make up our daily lives. The light from those distant galaxies has travelled billions of years to reach us, carrying information from the universe's youth, and we've built instruments capable of catching that light and learning from it. That's extraordinary, a testament to human curiosity and ingenuity and dedication. And it's also just the beginning, because Webb will continue operating for years, making new discoveries, revealing more of the universe's secrets, continuing the ancient human quest to understand where we came from and what we're part of. Let that thought rest gently as we move toward our close, satisfied that we've explored what we came to explore, ready now for rest and reflection, for letting the journey settle into memory and meaning. Thank you for staying with me through this entire journey, for spending these 2.5 hours drifting through cosmic history, through Webb's discoveries and the questions they raise, through contemplations of our place in the vast unfolding of space and time. It's been a privilege to share this exploration with you, wherever you are tonight, however you found your way to these cosmic thoughts. We've travelled together from the present moment back to the universe's youth, from the here and now to galaxies existing when the cosmos was just a few 100 million years old, seeing them not as they are today, but as they were more than 13 billion years ago. They're like carrying messages from a time before our solar system existed, before most of the stars we can see in the night sky had formed. We touched on the James Webb Space Telescope itself, how it works, what makes it so powerful, what it can see that previous telescopes couldn't. We explored the puzzles its observations have revealed, galaxies that seem too massive too early, structures too organised for their cosmic age, black holes that grew faster than models predicted. We contemplated the broader implications, what these observations might mean for our understanding of cosmic history, whether they require revisions to the standard model of cosmology or simply refinements to our models of galaxy formation. We considered the role of dark matter and dark energy, of feedback processes and chemical enrichment, of reionization and the cosmic dawn, all the complex physics that shapes how the universe evolves. And we reflected on meaning and perspective, on our place in cosmic history, on what it means to be conscious observers in a vast ancient universe, and how scientific knowledge connects us to the cosmos while grounding us here on Earth. The answer to the implicit question running through this exploration about whether Webb's discoveries disturb our understanding of the universe is both yes and no, a nuanced response that honours the complexity of the situation. Yes, in that the observations challenge our models, push the boundaries of what we thought possible, require theorists to revise their understanding of early galaxy formation. But also no, in that the fundamental framework of cosmology remains sound. The big picture of cosmic expansion and structure formation continues to hold, and the discrepancies are the kind of productive tension between observation and theory that drives science forward rather than catastrophic failures of understanding. Perhaps the answer is also that disturbance isn't something to fear, but rather to welcome, that having our models challenged is how we learn, how understanding deepens, how science progresses. The universe continues to surprise us, continues to be more interesting and complex than our theories quite capture, and that's wonderful. That's exactly what we should hope for, because it means there's still more to learn, still discoveries waiting to be made, still room for wonder alongside knowledge. If you enjoyed this slow drift through cosmic time, if these contemplations resonated with you, if you found peace or interest or both in this exploration, I'd be grateful for a like or subscription to support this work and help others discover these calm journeys through science and history. To those already subscribed, thank you for being part of this community, for valuing thoughtful exploration over sensational headlines, for spending time with these long, careful looks at how the universe works and what it means. Your presence here makes this possible. Wherever you are in the world right now, whatever time it is where you're listening, I hope you're comfortable. I hope your breathing has slowed and deepened. I hope the day's tensions have started to release their hold. I hope your thoughts have quieted or at least shifted into contemplative rather than anxious modes. I hope your body feels heavy and warm and ready for rest. Look up at the night sky, if you can see it from where you are, if clouds or city lights haven't hidden the stars. Look at those points of light, those distant suns, and think about how each one is a story of nuclear fusion and gravity, of cosmic evolution and chemical enrichment. Think about how the light you're seeing left those stars years or centuries or millennia ago. How you're seeing the past when you look at the sky. How every direction is a journey backward in time. And think about how those stars, those galaxies, all the structure we've been discussing, formed from simpler beginnings, from the hot, dense state after the Big Bang, from tiny fluctuations grown large through gravity's patient work, from hydrogen and helium converted into heavier elements through stellar alchemy. Think about how that process continues, how stars are still forming and dying, how galaxies are still evolving, how the universe continues its long transformation from simple to complex and eventually back to simple again. Cycles within cycles, patterns within patterns. All those distant galaxies that Webb observes, all those early structures forming in the universe's youth, they're part of the same cosmic story we're part of, the same physical laws governing their evolution that govern our sun and earth, the same atoms that make them up, that make us up, the same fundamental forces shaping their destinies that shape ours. We're connected to them across space and time, part of one continuous cosmic evolution, one universe exploring its own nature through physical processes that eventually, in at least one small corner, led to consciousness and understanding. In the end, what we're left with is not certainty about every detail of how galaxies formed, or why the early universe was more efficient at building structure than we expected, but rather something simpler and more profound. The recognition that we live in an extraordinary universe, one rich with structure and complexity, one old enough and stable enough to have allowed this complexity to develop, one that includes us and our capacity to observe and understand and wonder. That's enough. That's more than enough. That capacity to wonder and understand, that participation in cosmic evolution, that brief window of consciousness and awareness in a universe that will eventually return to simplicity. We're here now, able to observe and contemplate, able to build telescopes and gather light from the universe's youth, able to trace our origins back to the Big Bang and forward to an uncertain but fascinating future. Sleep well tonight, dream of galaxies forming in the ancient darkness, of stars igniting for the first time, of light travelling billions of years to reach our telescopes, of cosmic evolution unfolding according to physical law, beautiful and terrible and awe-inspiring in its vast patience. Dream of your own atoms' journeys through stellar cores and supernova explosions, through space and time, until they came together to form you, conscious and aware and capable of wondering about it all. Good night from this small planet orbiting an ordinary star. Good night from this brief moment in cosmic history when the universe is neither too young nor too old. Good night from this extraordinary present where consciousness can contemplate its cosmic origins and find both humility and wonder in what it discovers. good night.